Hello everyone, welcome to our session, Sensors and Observations. Vinay and I are pleased to be the chairs of this session. I'm Nastaran Saberi, a core modeler at GWF, University of Waterloo. My research focus is mapping lake ice using spaceborne SAR and deep learning while quantifying the uncertainties associated to observations and models. Vinay, over to you.
Hi everyone, I'm Vinay. I'm a PhD student with McMaster University, and I'm working on water quality monitoring sensors with a spatial focus on nutrient monitoring.
Thanks, Vinay. I would also like to introduce our session conveners, Professor David Rodolphe, University of Waterloo Chair in Groundwater, Professor Claude Duguay, University of Waterloo Research Chair in Cryosphere and Hydrosphere from Space, and Professor Ravi Selvaganapathy, Canada Research Chair in Microfluids and Professor of McMaster School of Biomedical Engineering. I want to start by acknowledging that we are participating today from traditional territories of the First People across the country. Here is Kitchener-Waterloo. I acknowledge that I'm on the Haldimand Tract land that was promised to be Haudenosaunee of 6 nations of Grand River. The Haldimand Tract is within traditional territory of neutral Anishinaabe and Haudenosaunee people. A few quick housekeeping notes. It's going to be a fast-paced meeting that will be touched on various aspects of our research on sensors and observations. We will begin with a 20-minute keynote from Jay Famigliati on the emerging trends and opportunities in Canadian remote sensing. This will be followed by 4 further presentations on a range of new water monitoring technologies. If there was a time at the end, we'll try to take a few questions, but having said that, if you have any questions at any time, you can post them in the Q&A and we will collect them and try to address them. This webinar will be recorded and will be available for later viewing. And you can also open the captioning and use the button at the bottom of your screen to enable it. And last note, please join us on the social media using the hashtag GWF2021. I would like to note that we expect all conference participants to abide by a code of conduct that you have access to on the homepage of the conference. Without further ado, I will introduce our first speaker while he gets his slides set up. Our first speaker is Professor Jay Famigliati. He is the Executive Director of the Global Institute for Water Security at the University of Saskatchewan, and he and his research team use satellite observations and develop computer models to track how freshwater availability is changing around the world. With this, I will take it to Jay, please.
Okay, thanks very much, Nastara. And I'm still waiting for my screen sharing to be enabled.
Awesome. Just 1 second.
Sure. And I'm glad that you said it was fast-paced because I have way too many slides and I've had way too much coffee, so it's a dangerous combination. But let's hope that it's fun. Okay, I assume Nastara, you're the only one I can see or could see. You can see this okay? Okay, fantastic. So thanks everybody. So let me give you the sort of high points now and then at the end. Our hydrology in Canada is changing really, really fast. I think faster than we're able to keep up with it. So of course, remote sensing gives us this synoptic scale view. It allows us to quantify these rates of change and try to understand their drivers. There's so much work that remains to be done to understand how these remote measurements, and they could be drone measurements, they could be aircraft, they could be satellite, what they mean, how we can integrate them with our ground-based observations, with our predictive models. It's really exciting times, but also challenging times. We have to keep in mind that these results and tools and innovations and everything that we come up with sometimes need to be co-developed, almost always need to be shared. We need to go beyond academics with stakeholders to maximize their impact. There's a real urgency today with what we're seeing from remote sensing. And GWF really provides a perfect vehicle to start to initiate these connections. So we have to keep on going after the program is over. So let's start with so overview, big picture, emerging trends, opportunities for measuring. I'll focus on storage changes. That's sort of my wheelhouse. So snow, surface water, soil moisture, groundwater, and then some closing thoughts, which are actually my opening thoughts as well. So some of the trends, I'll focus on my work with GRACE, or my team's work with GRACE. This is a very compelling picture that emerges from the GRACE mission. These colors show the trends over the lifetime of the GRACE mission, 2002 to 2017. Reds are losing and blues are gaining. And let me sort of break it down for you. This is background pattern of the wet areas getting wetter and the dry areas getting drier. And so we see these trends, and those are largely driven by climate change. And sort of sprinkled on top of that background pattern, we have these hot spots for ice sheets melting, glaciers melting, increasing flooding, increasing extremes of flooding and drought, and groundwater depletion, which many of you have heard me speak about many times over the past almost decade now. So it's a really challenging picture that we have to contend with and understand what's going on. This is against a it's probably against my better judgment to have included this slide because it requires a fair amount of explanation, but we're looking at all the water in the world from GRACE. Okay, so we just saw the spatial pattern of how things are changing on land. This is now one line for one time series for all of the ocean, right? That increases ocean mass increasing. So seasonal variations, sort of ocean has a wet season and a dry season, increasing mass. And where's that increasing in mass coming from? Well, it's coming from Greenland melting, that's the red line. From Antarctica melting, that's the black line. And well, you know what? This is a recent result. The land is now contributing just as much through ice melt, through snow melt, through groundwater depletion, which some of which ends up in the ocean, is now contributing actually more than both of the ice sheets on a millimeters per year basis. And so Canada has a big role in that, of course, because we're melting away here. Here's the so-called warming stripes that show graphically how temperature has increased, especially over the last couple of decades. And many of us have seen the Canada Climate Change Report with the temperature maps, a lot of warming in the winter. We all have heard by now Canada's warming at twice the global rate, Northern Canada at 4 times the global rate. Here in the prairies, we're at 3 times the global rate. So, with that comes a lot of melting and a lot of change. So with remote sensing, we have an opportunity to quantify that. Let's dig in a little bit to that trend map I showed you, to what's going on, what we're seeing from the GRACE mission. So now we're looking at the time series, right? So wet season, dry season, monthly data, okay? And we're going to look at some of these spots that stand out on the map. So we're looking at Alaska and northern British Columbia with a downward trend. We're looking here in the Athabasca region, which is somewhat, so this one is largely driven by melting snow and some groundwater depletion down in southern BC. This one, big drought happening there. Could also be some water use for resource extraction. Of course, as we get close to Greenland, that area is just melting away. But then as we swing around across the southern tier, way down south, Quebec, we see some increase, and Toronto, some increasing water storage. And this big spot that's really been persistent across much of the GRACE time period, I think that there's some flooding here in the upper Midwest that's been going on for a long time, but also when the GRACE mission started, there had been a pretty big drought up here in Canada, in Alberta, and Saskatchewan. So in a relative sense, there was an increase, but now we're starting to see that flop over here. So, there's another way to look at it. And this one I find a little bit more disturbing. If we go and look by basins. So this is really Alaska, much of the Yukon. We see that downward trend, okay? In the Mackenzie, we see that downward trend. In the whole sort of broad, huge Nunavut region, we see that downward trend, right? So this is really the signature of the ice and the snow and the permafrost melting. The Gulf of Alaska, so these green blocks here, really decreasing. And the Fraser, also showing that decrease. So, you know, a lot, when we look at the basin scale, we're seeing a lot of the decline of the availability of water. And so, you know, we need to really look at these and try to unravel what's going on. You know, what's happening with snow, what's happening with surface water, what's happening with groundwater, what's happening with precipitation, evaporation, stream flow. There's a lot of work to, to be done. So I just want to go through some of the missions that I've sort of been involved with, either directly or tangentially, and try to highlight their importance. I'm not going to try to cover everything again. Can't do that in 20 minutes. So, you know, some key, I wanted to focus on the storage mission. So if we think about what we see from GRACE, it's the change in total storage. That's the snow, surface water, soil moisture, and groundwater. So that's what I want to talk about today. So talked a little bit about GRACE, and I'll talk a little bit more in the groundwater context later on. Chris is going to talk about the snow mass mission. Here's our friend Gurdeep Pandher, the Bhangra dance guy, who's become so famous, maybe more famous than Justin Trudeau because of his Bhangra dancing. He's incredibly happy if you haven't watched it. And so this is how we're going to be if we're going to get a snow mass mission. We'll be dancing right along with him. If you haven't seen his YouTube videos, it's a must. SWAT mission, surface water and ocean topography. We have more surface water here in Canada probably than anywhere else in the world, a really important mission for us. And SMAP, the soil moisture mission, which many Canadians are already involved with. So snow water equivalent, you know, in my humble opinion, snow water equivalent is one of those holy grails of remote sensing. That's because we really need to know not just the extent and not just the albedo on the surface, but we need to know the snow water equivalent. And that involves going beneath the surface, and that's difficult. And so Chris is going to talk about how you can do that with a radar mission. Really challenging also just on its own, even with difficult to measure, in particular difficult to measure in the mountains logistically. There's a lot of water up there. We need to know how much water is there. It's much like groundwater. Like once you get below the surface, you can't really see what's there, and it's really critically important. Here's another paper that Chris was involved in that shows how, you know, we know the snowpack is shrinking in space and time, and so here's the duration that's decreasing from the 50s up to the mid 2010s, and the annual maximum snow depth anomaly. So, you know, the snowpack is shrinking away, and Chris and his colleagues are showing it with observations. You know, we can do a great job with airborne remote sensing. Here's some slides from Tom Painter with his Airborne Snow Observatory in the Tuolumne Basin. You know, it's fantastic stuff, but we need to know this globally, and we're not going to be doing it with a fleet of aircrafts or a fleet of drones. They're super important for a local scale, regional scale, but we really need that mission that Chris is going to talk about. To me, again, it's one of those holy grails. Surface water, you know, I just mentioned that Canada, you know, I just tried to Google it before the talk. We must have more surface water by area than any other country. So a mission like the surface water and ocean topography mission is critically important for us. It's going to provide a global inventory of the heights of the larger terrestrial water bodies greater than 250 by 250 meters, and rivers whose widths exceed 100 meters. It's going to give us the heights, inundation extent, so that we can get that global storage change, that sort of waxing and waning of surface water coverage all over the world that we've never had. So that is very cool. A lot of science, a lot of important applications. River discharge will be an estimated product, and it'll give us this, I think, unprecedented view of surface water change. Here's a slide from Larry Smith just showing some work that was done in the Above campaign. And this is one from North Saskatchewan River Basin. So they flew measurements of the river heights and compared them to observations from GPS and from pressure transducers and from a boat survey. So the blue lines are the air SWAT measurements, and all the others, the red, the orange, and the yellow, are observations. So great potential there, and thanks to Larry Smith for that slide. Soil moisture is something that I've been involved in for a long time, going back to my graduate school days, that Canada's been involved in for a long time. and super, super important for Canada for agricultural applications, for drought applications, for understanding land-atmosphere interaction, for improving their representation in models, for fire risk, and so on. So SMAP was launched in 2015. I had the good fortune to be at that launch, and it maps globally the soil moisture in the upper 5 centimeters of the soil surface every 3 days at a 40-kilometer resolution. There were initial plans to have higher resolution, and the radar that would have been accomplished by the inclusion of the radar broke down pretty quickly. We're now looking at replacing that with Sentinel observations to recover that higher resolution. Anyway, so far so good with SMAP. Here's some work from Aaron Berg, and there's a great community here. Aaron Berg's at Guelph, Catherine Champagne at AFC. Got a meeting later today with Alexander, Roy, and Aaron and Ramada Magaji. And so here's some sites that Aaron has set up. These are berm sites up in Prince Albert area of Saskatchewan. And so he's been looking at setting up a validation site or sites across the prairies and integrating radar, trying to add resolution, and lots of great work that's been going on in Canada. Here's a comparison of retrieved soil moisture to retrieve from algorithms remotely, retrievals compared to observations of soil moisture. So good fit here. And here's an application from Sarah Sadri and Eric Wood's group at Princeton, looking at an integrated near real-time SMOS is the French soil moisture satellite, soil moisture, ocean salinity, sort of an index, like looking at a percentile basis of abnormally dry, different levels of drought, moderate drought, severe drought, and so on. And so it's the SMAP-based index on the left compared to an AAFC product on the right. And so good comparison. Tremendous potential there for fires, for flooding, for forecast, like the 3 or the 4S: forecasting, fire, flooding, food. Really important for understanding water availability. I just want to pivot to the root zone. So that was surface soil moisture. What we really need to understand is the deeper soil moisture, the upper half meter of the soils, where the roots are, where the plants get their water. And so this is work that's been, this is Mata Magadam from USC's work, mapping root zone soil moisture up at the berm sites in Saskatchewan. This is about a 90-meter resolution. This is really, really difficult work, right? There's a lot of things. Once you start penetrating deeper into the soil, probably as Chris is going to talk about with snow, it gets more challenging because there's more things that it's an active signal. It bounces off lots of different things. And so you need to make lots and lots of measurements. So really challenging, but really, really important. In my opinion, we need to be pushing for this in Canada and trying to map this, right? Map this across the prairies, map this across our agricultural regions. So big opportunity there. Groundwater, a lot of you have heard me speak about this for many, many years. I've been using the GRACE mission. I won't take the time to really explain it other than just say it's more like a scale than it is an optical satellite. So it's weighing because of gravity changes, the mass changes on the ground. Here's some work that we did in California, or doing. This is an update actually. So this is actually a time series of groundwater from space going up to almost up to the present. In the Central Valley here in California. It's the kind of thing that can be reproduced and has been reproduced all over the world, including in Canada. And you can combine with other data like we did here in California, looking at this long-term picture, combining with USGS well observations in red and the GRACE data in blue, going back to the early 1960s, you get to see this long-term picture of decline that's unfortunately happening all over the world. Those colors in the background represent climate, whether it's very wet, like blue, or very dry. So, little recharge during the wet periods and a lot of decline during the dry periods, which seems to be the way that a lot of these aquifers are managed or unmanaged, but the water's utilized in the global south. And that's something we want to try to avoid here in Canada. Here's some work from Huang et al. Up here in Canada, looking at comparison of grace shown in blue to a bunch of well observations. So there's been a fair amount of work done with grace data all over Canada. And just one we just pulled off that Xander Huggins, who's a graduate student that I share with Tom Gleason, just pulled out this morning for the Saskatchewan-Nelson River Basin. And this, you can see the increase, this is sort of looks very much like the Saskatchewan Basin signal. But we can see, and we see it in the total water storage signal as well. There's this drop off that's happened over the past couple of years that we have to start watching. And we know we're headed in a drought period here. So this stuff is quite useful, especially when blended together with other data sets and integrated into models. Closing thoughts are these. The human fingerprint on the freshwater landscape through climate change, through ice melting, through changing extremes, and through water management. And I'll show you a reservoir storage slide in just a second, but groundwater, lack of groundwater management, building of reservoirs, it's the dominant force. Like these spots here, these are all, climate change. Extremes are exacerbated by climate change, and the groundwater spots. It's a dominant force that's changing these patterns of water availability, and it's happening really fast. And so there's, this urgency with respect to us in academics, in terms of getting the message out, in terms of understanding what's going on, in terms of integrating what we find into the decision-making stream, impacting policy, combining with models. This is great information. In many cases, we're not going to get the big picture unless we use satellites, and we need that big picture once we get outside our region. We really need to understand what's happening at the provincial scale and the interprovincial scale, river basin scale, and continental scale. Just another look at the human, the human side of it. This is the GRACE data mapped to this template of aquifers, and over half of these are the UN aquifers. Over half, there's 37 that are recognized by the UN. Over half are being rapidly depleted now. So 20 of these 37, not great. Here's a slide from Larry Smith, who is using an ICESat satellite as sort of a precursor to the SWAT mission. And he was looking at surface water variations in the reservoirs and found that 57% of the seasonal surface water storage is coming from these human-built reservoirs. So we're having a huge impact. We can see it in the satellites. So in closing, this is the same as the opening thoughts. The hydrology is changing really rapidly. Okay, and I'm just scraping the surface here today. I've focused on some of these storage change missions. Remote sensing allows us to see these things, to quantify these rates of change. Tremendous amount of work. I'm both a little depressed by the situation, but excited about the opportunities to do the work and to make a difference. So we need to be integrating these measurements with ground-based observations, with predictive models, and really communicating what we're finding. We need to be co-developing and sharing our information. And again, GWF, I mean, what a great program, and just a tremendous opportunity and great fortune for Canada. So I'll stop there. Thanks very much.
Awesome. Thank you so much, Jay. Great job on time management. And thank you so much for the great presentation. Actually, the snow retrieval piece was actually nostalgic for me because I used snow water equivalent retrieval using passive microwave during my PhD. And we have a little bit of time now for some questions, and I encourage participants to post questions on Q&A box, and we can answer some of those. Or I guess I can't see the participants, so it's only the Q&A, and there is no open Q&A so far.
It's okay if there's no questions. I need to catch my breath. I went so fast.
Yes. You can follow on the next presenters. Vinay, please. To you.
Hello, everyone. Next in presentation line, we have Dr. Kiana. Her current research interest is machine learning application in retrieving biogeochemical characteristics of water bodies. More specifically, she'll be talking about algal blooms from hyperspectral imaging. Over to you, Dr. Kiana.
Thank you for the introduction, Vinay. So is my presentation coming through okay?
Yeah, we can see it.
Okay, so my presentation is about implication of hyperspectral imaging in the Canadian water microsatellite mission concept. And in this presentation, I will first briefly talk about the concept design of the mission and the survey that we had done back in 2019. And then I will focus the presentation on only the hyperspectral component of this mission and how it can help improve the monitoring of algal bloom. And then I will present part of the proof of concept hyperspectral study. And I will also show examples of a flight line of hyperspectral airborne coverage from Lake Erie Western Basin that we have collected back in 2019 in a collaboration with NRC. So as we know, water supply and water quality are the two critical issues relevant to water resources in Canada, but also globally due to climate change. And more specifically in Canada, coastal and inland waters are under increasing pressure from human impacts because of the climate change that will bring social and economical consequences. So there is a need from various government departments and academia and industry for a satellite mission to better support the management, monitoring, and also the research on inland and coastal waters in Canada. And the water microsatellite mission that is being proposed here is aiming to better prepare the end user to study and understand this emerging spectrum of water future issues. And it has basically three main components: the hyperspectral component with high spatial resolution and more than 400 bands, the GNSS reflectometer on it, and also there is an opportunity for two-way communication with water quality monitoring networks on the ground between satellite and the modems on the ground. And we had conducted a survey in 2019, and our survey participants were from different parts in Canada and also globally. And more than 20% of participants, their research were focused on lakes, reservoir, and ponds, and they declared that an increase in temporal, spatial, and spectral resolutions of the upcoming satellites will help them with major improvements in their research. Now I will focus only on the hyperspectral part of this mission and how it can help with the monitoring of algal bloom. So why algal bloom are important? Because the distribution of phytoplankton in space and time, as well as their species and the composition of these species, are basically indicators showing the biodiversity and the health status of aquatic ecosystems. If we understand the dynamics of phytoplankton, then we can understand how these aquatic ecosystems are responding to climate change and land use, land cover changes. And the primary concern about water quality in inland waters and coastal waters is the increasing presence of algal blooms, which is typically triggered by increase in temperature and the available nutrient levels, such as phosphorus and nitrogen. And as the figures on the right side of the slide shows, they can affect tourism, recreational and drinking water, and also real estate. HABs has been the largest cause of marine salmon mortality in British Columbia, and Lake Erie Western Basin regularly experiences this harmful algal bloom every year. And back in 2014, the city of Toledo experienced the contamination of its drinking water supplies because of the presence of cyanobacteria HABs in Lake Erie. So monitoring of harmful algal bloom are important, and aquatic remote sensing has been proven to be an efficient and convenient monitoring tool because they provide high degree of spatial and temporal resolution over extensive spatial scale. And this will help us to monitor magnitude, extent, frequency, and duration of HABs. And through more than 2 decades of proof of concept hyperspectral studies, it is anticipated that hyperspectral imaging will enhance the accuracy of remotely sensed water quality products because the fine spectral resolution that is provided by hyperspectral imaging will help us to capture the subtle spectral features of phytoplankton and distinguish different types of them. And as a proof of concept study, I will present only the key, basically the key conclusions of this research here, but it has been submitted. It was a collaboration between different colleagues from around the world, and we collected in situ data from South African Reservoir, Western Lake Erie, Indiana Reservoir, Fremont Lakes, more than 60 lakes in Spain and also in the Netherlands. And we have collected, so they basically collected field measure radiometry, and they provided us with remote sensing reflectance for each of these regions. And as you can see, the shape and the magnitude of remote sensing reflectance in each lake is different. For example, the magnitude of reflectance in Fremont Lakes is less, and it's because of the more levels of dissolved matters in this study site. And they also collected chlorophyll and phycocyanin in the field. And these plots are basically showing how what is the density, what is the distribution of these in each field separately, and for all data together. And we have more than 900 samples, and the phycocyanin concentration when all data is combined was around 59 milligram per cubic meter. And another way to look at this data set is not only by separating them based on their study site, but also based on the optical water type that is available within this whole data set. And because the optical water type differs based on the water quality status, and this can change not only from one region to another, but also within one single study site from one location to another. So that's why we applied K-means clustering algorithm on this whole data set, and we retrieved 3 classes. And the first class shows lower concentration of phycocyanin and chlorophyll. And this is the average spectra in this class. The second class shows higher levels of phycocyanin and chlorophyll, and the spectra shows more prominent peaks and hills compared to the first class. The third class shows, although lower phycocyanin and chlorophyll values compared to class 2, but as you can see, there is higher levels of remote sensing reflectance in the longer wavelengths, and this is because of higher levels of suspended matters. And in this plot, we are calculating the correlation of remote sensing reflectance in each band versus phycocyanin concentration. And as you can see, for the first class, the highest correlation occurs in the shorter wavelengths. For the second class, it occurs around 620 nanometer, and 620 is a well-known phycocyanin optical feature. It has an absorption peak in these wavelengths. And the third class, the highest correlation occurs in this region. And so hyperspectral is basically helping us to capture the region of the spectrum that is contributing the most into phycocyanin retrieval. But as this plot here shows, multispectral satellites, the ones that are currently available, are not necessarily covering this range. For example, between multispectral that is currently available, only OLCI covers 620 nanometer. The future Landsat mission is called Landsat Next. The instrument on it, we called that instrument OLI Plus in this study. That will also cover 620 and 650 nanometer, which are the two distinct dual optical feature of phycocyanin. So using this matchup data set, field measured remote sensing reflectance and field measured phycocyanin data, we resampled the hyperspectral to the band configuration of our available some examples of available hyperspectral missions such as HICO and Prisma, and also to the band configurations of multispectral missions such as OLCI, MSI, OLI, and OLI Plus. I did not bring the numbers here, but the statistical indicators shows that when we apply the multi-layer perceptron on hyperspectral data, they will perform better than multispectral missions to retrieve phycocyanin. We tried other type of machine learning algorithms too. I did not bring the result here, but MLP multi-layer perceptron was performing the best. And then after hyperspectral data, the best performing one was OLCI, the next was OLI Plus, and then MSI, and the worst was OLI. Another factor to consider is that when cyanobacteria is dominant between other types of phytoplanktons, OLCI can perform as good as hyperspectral data. And when cyanobacteria is not dominant, hyperspectral performs best between all other scenarios. And this figure here is showing the specifics of past, current, and future hyperspectral satellite missions, the number of bands and revisit frequency of them. And PACE is the next NASA mission. And Canada is also working on WaterSat mission, hyperspectral mission, and WISE and CASI are the two instruments on board of this hyperspectral mission. Sorry, WISE will be on board of WaterSat mission, and WISE is basically the new version of CASI, and the specifics of WISE will fall somewhere in here. So it's compared to PACE, it has a longer revisit frequency, but better spatial resolution. So it will be a good complementary to what PACE will provide us. And this table here is summarizing the specifics of WISE. And for example, the spatial resolution of it is 100 meter. And back in 2019, there was a HabGrab Day. It was a collaboration with more than 15 Canadian and American organizations. University of Waterloo Global Water Future Program also collaborated, and we flew WISE and CASI hyperspectral sensors on NRC Twin Otter aircraft at the same time as the crew, on the ground. They were these red dots in these maps are showing around 170 stations on western side of Lake Erie, and crew were collecting water samples from these stations. And NRC flew over these stations. The green lines are showing the flight lines. And at the same time as NRC, and NOAA GLER and NASA Glenn also flew their hyperspectral sensors. And right now, so these images are from a view from the aircraft window from Mayumi Bay State Park. And this is summarizing all the stations. NRC hit around 150 of those stations on that day. And this is an RGB WISE image produced from the same area. And NRC right now is in the stage of pre-processing these hyperspectral images. And this is just an example they provided us. This is a flight line, and this plot basically are showing the remote sensing reflectance from 4 selected points in this flight line, one on parking lot, the other one is located on a beach, and one near shore water and one offshore water. And both WISE and CASI are capturing the features of, for example, phytoplanktons in the spectrum, but WISE in the blue region is saturated for beach and the parking lot. So NRC is still working on the radiometric correction of these WISE data and also the atmospheric correction. And once this data becomes available from NRC, we will go for the next steps, which is basically producing water quality maps using these hyperspectral images. And we will also plan to work with our collaborators and compare it between these hyperspectral sensors. And with that, I would also like to thank my collaborators from NASA, Environment Canada, NOAA Galera Lab, and NRC. And thanks to you for listening.
Thank you, Kiana, for such a nice presentation. For the sake of time, I'll not be opening the floor for the questions, but feel free to put your questions in Q&A section, and all the speakers are going to put their answers there. So for next presentation, we have Chris. Chris is a research scientist with Climate Research Division of Environment and Climate Change Canada. And today he'll be talking about development of terrestrial snow mass mission. Over to you, Chris.
Great. Thanks very much, Vinay. Can you see
Just
my
one
screen
second.
up?
I think Claude has a question. He raised his hand.
Yeah.
You're mute.
No, it is fine. It is fine. No.
Oh, okay. Sorry.
Okay, so can you hear me and see my screen okay? Yeah,
Sure.
Okay, great. Well, thanks for joining everybody. And Jay is going to save me a little bit of time because he did a great job in expressing how important snow mass or SWE is. So that helps frame my presentation a little bit. So I'll be presenting on a new satellite mission that we're developing at Environment and Climate Change Canada in close partnership with our colleagues at the Canadian Space Agency and with really important contributions from industry across Canada as well. And just by way of background quickly, there was an assessment of options performed by industry a couple of years ago now to look at how can Environment and Climate Change Canada address this big gap we have in snow mass observations using spaceborne technology. And at the end of that study resulted in a focus on KU band radar as the technology that's best suited to meet these needs. And that technology also builds on some really important progress that was made a few years ago now in the scope of an ESA mission called Core H2O, which was ultimately not selected for implementation, but made it quite far through the competitive process. And so the science community learned a lot from that. So I'm presenting on behalf of quite a large group of folks at Environment Canada and CSA who are working on the mission. So just to put up front what we're trying to do. So our current observation gap, not just in Canada, but in all snow-covered areas, is sort of moderate resolution, but rapid revisit, satellite-derived information on snow mass. We want to provide that across Canada at 500-meter grid spacing, repeating coverage of the whole country every 5 to 7 days. And so with the KU band radar concept that I'll be describing today, we can achieve that. So it's quite a wide swath instrument, but it will provide, again, at 500-meter grid spacing, full coverage of Canadian snow-covered areas every 5 to 7 days. And from these KU band backscatter measurements, we will be able to retrieve information on the wet-dry state of snow cover and the snow water equivalent. So I think Jay framed all this really well, but I mean, fresh water from snowmelt really is a vital, valuable commodity to people across the country. And we can currently derive some information on snow water equivalent from satellite remote sensing. Probably the state-of-the-art product across the Northern Hemisphere is the European Space Agency Snow CCI product. That's what I'm showing in the top left here. That's the climatology on the top and the long-term trend, multi-decadal trend across the bottom. So it's a very useful data set at sort of the continental scale, but the products are coarse, 25-kilometer grid spacing. Mountain areas are masked out. So if you look at the trend map here, all these gray areas in Western Canada, there's no information because the spaceborne measurements are just too coarse. And this retrieval method really does rely also on a background field of snow depth observation. So it uses remote sensing, but it is assisted greatly by surface observation. So it's really it's not a perfect product. We also know that fresh water supply from glaciers in Western Canada, unfortunately, is looking to be a finite resource. So these glaciers will largely disappear by the end of the century under current climate projections. So this will increase even more the pressure on fresh water from snowmelt as a resource across the country. So what has emerged in recent years? What's the timing for why this mission is emerging now? Well, we know, as I've already mentioned, that snow is of value to Canadians. It also, on the flip side of that coin, poses a risk through usually spring flood damages. So the vast majority of federal disaster assistance costs are related to flood events that are fed greatly by snow. But as well, at Environment Canada, we're entering in, supported by programs like Global Water Futures. We've really advanced operational land surface modeling, so our systems could now ingest data from a mission of this sort. We've moved forward a lot over the past decade in understanding how Ku-band radar responds to snow, and industry has made some great strides in developing sort of low-cost, low-mass spaceborne radar systems. So collectively, this landscape means we hope at Environment Canada to acquire these data to answer two sets of questions. Really, the first is focused more on climate services. So we want to answer quite simple questions like how much water is stored as seasonal snow and how does it vary in space and time. And then from the prediction point of view, we want to feed models with information from the mission to answer questions like what is the contribution of snow to the water cycle and how well can we predict it. So why Ku-band radar? I'll have to go through this fairly quickly, but these are just some proof of concept plots that show how the signal at this radar frequency interacts with the snow volume. It's scattered by the snow volume and is sensitive to the snow mass. So these are from tower-based measurements with a Ku-band radar in Finland. I'll start with the plot on the left. The solid and the empty symbols represent 2 different years. Snow water equivalent on the x-axis and backscatter on the y-axis. And the lines are what radar models suggest that how the measurements should evolve over time. And you can see they do fit this curve quite nicely where backscatter change is proportional to the snow mass or the SWE. This is only 2 years of data. If you plot multiple years of data beyond this from the same tower measurements, things get a little bit messier. And the reason why that is because Ku-band radar is sensitive also to the microstructure of the snowpack. So by microstructure, we mean the snow grain size and shape. And so what the middle plot shows is as we evolve to deeper snow, moving to the right, but we change the grain size, the snow microstructure, that's what each of the colored lines corresponds to, we also see a change in the backscatter. So we get this kind of ill-posed retrieval problem where backscatter is sensitive to the snow water equivalent, but also to the snow microstructure. So that means we have to be quite clever in how we address this. The plot on the right is results from a colleague in Finland. He led a group there that used these same tower-based measurements to look at how we might retrieve SWE. And it turns out if you can constrain the retrieval with a first guess information on the snow microstructure, 2 different methods are shown with the 2 different colors in this plot, then you can produce some skillful retrievals. So what this means is we want to use the radar measurements in partnership with other information on microstructure to estimate the snow mass. So a little bit on the technical concept. There's been no previous Ku-band SAR mission in space. This would be the first mission of its type. There's been scatterometers at Ku-band, but not a SAR. Canadian industry scoped and has developed what we're calling an explorer scale mission. That means it has a strict and managed cost cap. So we want to do this at a lower overall cost, thereby reducing the risk, but still advancing the technology in a new direction and allowing us on the science side to prove that this is a viable mission concept. We will acquire 2 measurements at 2 different Ku bands, as indicated here. I already mentioned it's quite a wide swath, 500-meter grid spacing, and the SAR will operate quite a bit each orbit. About 25% of each orbit, the radar will be turned on. That's quite a bit for a SAR mission of this type. But we hope, again, to launch this in the future and get 3 winter seasons of data. This is what the coverage masks look like. So the colors on the left tell you how many days between repeat coverage. And so it's about 3 to 5 days across most of Canada, even less as you move further north. And most southern regions of snow-covered area, it's more like 7 days. So it's 5 to 7 day coverage. The plot on the right is the 7-day repeat coverage at the 250-kilometer wide swath. We will also have a 50-meter high-resolution imaging mode. So in mountain regions, for instance, that's a big advantage. Unfortunately, when you change the resolution, you narrow the swath. So for a couple of watersheds here, we're just showing what that swath resolution trade-off, coverage trade-off looks like. And so we would gain in the footprint size, but we would lose in the coverage. So that's just give you some perspectives on what the coverage looks like. I want to spend a little bit of time, the last 5 minutes here, looking at the sort of flow chart of how we want to analyze the data. And really, there's two main things that we want to do with the backscatter data from this mission. Number one is to use it to estimate SWE, so produce maps of snow water equivalent at a spatial resolution we've never achieved before across all of Canada. And also assimilate the backscatter directly into the Canadian Land Data Assimilation System, which is called CalDAS. And that would then in turn inform the models that we use to produce weather forecasts, but also to produce other predictions like stream flow, which is obviously sensitive to snow cover. So we have sort of two sides of the flow chart here relating to those two things. So I'm going to try to get this animation going. The first thing we need to do is separate dry snow from wet snow. This is a C-band radar mosaic that my colleagues David Small and Steve Howell have produced, and I'll just try to stop it here. You can look at the ice caps on Ellesmere Island and just watch the backscatter change over these ice caps. That's the melt advance moving up and down these ice caps. So all this to say that radar is very sensitive to the wet-dry state of the snowpack at all frequencies, and so we could use the KU band data to distinguish dry snow from wet snow. We also need to know something about the snow microstructure, as I mentioned earlier. So we can use physical snow models to do this. So the plan is to use the operational physical snow model at Environment Canada. I'm just showing an example of surface snow grain size on the left here. We could then use this model to produce estimates of snow microstructure. That would then inform our SWE retrieval. So we have that first guess information that we need, supported by our snow modeling colleagues. This would then be used on one half of our plot here to assimilate KU band backscatter directly into CalDAS. Now, this is already done at Environment Canada for improved soil moisture analysis. In this case, they ingest L-band passive microwave data from the SMOS and SMAT missions, both of which Jay mentioned in his talk. We need to tweak CalDAS a little bit to do the same thing for KU band radar for snow, but the plan here would be to assimilate this information, much like we've done for soil moisture, but to improve the analysis for snow. And then finally, we know there's areas in Canada where the forest will be dense when the snowpack is wet, where we can't retrieve snow mass directly from the radar mission. So the plan here would be to merge the radar estimates from the satellite with model information on snow mass. And so what the map on the left shows for the Nelson Churchill, the green areas are where we have openings, open land, either gaps in forest cover or prairie land cover, where we could lean heavily on the radar retrievals. The red and the white are areas where the forest is probably too dense. In those places, we would lean on the model and then merge everything together to get this seamless national coverage. We have some airborne data that we're working with. We hope to get more. I won't have time to talk about this, but we are using, in addition to tower-based measurements, some airborne data. Some measurements made by our colleagues at UMass over the Trail Valley Creek site in northwestern Canada. So finally, the summary and the path forward. We have this Explorer scale mission concept. We're quite excited about it. I think it's going to push industry and science into some new spaces. The phase 0 industrial study actually finished last fall, but we've now successfully moved forward to the next phase at CSA. So we're in a pre-development planning phase, as it's called. And during this planning phase, we'll be developing a mission simulator to produce synthetic KU band backscatter data. CSA is also investing in the next phase of technology development for the KU band radar with our partners in industry. We hope to get more airborne measurements in the coming field seasons. Hopefully we can get back out in the field soon. I just want to highlight that really our ongoing engagement with partners is really fundamental to the mission. I won't go through them here, but they're listed on this slide, some of our main partners. This engagement has really been vital in successfully moving the mission forward. We're still some years away from a launch of a mission of this sort, but we're excited with what the landscape looks like. So I think I'm out of time, so thanks for your attention. And I'll stop sharing my screen, Vinay.
Thank you, Chris, for keeping just under the time. So we are on time. Yeah. So I'll not be opening the floor for questions again, but feel free to put your question like questions in the Q&A section, and the speaker is going to answer those questions. Next up, we have Ravi. Ravi is working on different things like environmental sensors, diagnostic sensors, and today he'll be talking about metal ion pre-concentration and detection using super absorbent polymers for water quality monitoring. Over to you, Dr. Ravi.
All right, thanks, Vinay. Hopefully everybody's able to see the slides. So thanks
Yes.
for this opportunity. And today I'm going to present on behalf of my student, Mohammad Fatala, as well as Johnson. Both have worked on this nice and elegant technique. So unlike the previous speakers, I'm going to talk low tech rather than high tech. What we have done is to try to develop an elegant technology that will help visualize heavy metal contamination and potential toxicity for resource poor settings. So the title of the talk is Calorimetric Sensing of heavy metals. So I'll start with this slide here. So people of a certain vintage, like myself, would remember this movie, Erin Brockovich. It's starring Julia Roberts. So the crux of that story was Erin was a legal assistant, found contamination in the local settings of hexavalent chromium through her own efforts in terms of testing the environmental water, and then took on Pacific Gas and Electric, and was successful in court and prevented the environmental contamination from that source. And by the way, this picture here depicts the real Erin Brockovich. Let me pull up a laser pointer. So that sort of points to the importance of monitoring the environment, particularly for heavy metals. Heavy metal effect on the human body is often associated with its high toxicity. But it is important to also remember that some of these elements such as iron, zinc, and cobalt are essential for our body, but can be toxic at higher concentrations. Others like lead, mercury, and so on are highly poisonous even at trace levels, can cause things like cancer, neurodegenerative diseases, and so on. So these materials are non-biodegradable. They tend to accumulate in organisms. So things like fish and so on bioaccumulate these from the water, and when we consume them, or when we consume the water directly, they tend to bioaccumulate in our bodies as well. What we are also finding is because of various kinds of stresses by humans on the environment, industry, agriculture, and so on, there's more and more accumulation of this in our ecosystems that needs to be monitored. So in terms of water quality monitoring, World Health Organization has declared heavy metals as a priority substance to be monitored. And there are environmental limits associated with that. And here is a listing of those limits. What I would like to point out here is the concentrations at which they need to be detected. So some of these, like lead and mercury, need to be detected at a few ppbs, and that is an extremely low level. Just to put this in context, what a ppb is, so if I take like 1 gram of gold and try to come up with a few ppbs of this, I have to dissolve that gold in a swimming pool of water, right? So that's how low concentration this ppb is going to be. And in order to do that, we have rather expensive pieces of equipment which can take this sample at very low concentration. So things like inductively coupled mass spectrometers, or optical emission spectroscopy, for example, where you can use a plasma to actually ionize the metal ions, strip away water molecules associated with it, and then either measure its mass using mass spectrometry, or look at the optical emissions associated with that. Or you can use even more fancy techniques like X-ray fluorescence spectroscopy, neutron activation analysis, and so on, in order to do that. So what this means is that it necessitates somebody to take a sample, send it to a centralized facility that has these expensive equipments. It also has these trained personnel, and that increases the cost of these analysis. That does not allow one to do actual in-field measurements and real-time kind of measurements. So what we need in order to democratize this kind of field sampling is a simple and an elegant method that that is low cost, doesn't require a lot of expertise to do that measurement, and therefore it is in some ways automated and also can accurately measure at very, very low quantities, right? So these are all some of the issues associated with current ways of measuring these heavy metal ions in liquid samples. The alternative to that would be calorimetric sensing, right? So everybody would have seen these examples of pH paper. So there's a very simple transformation in color associated with the analyte that is of interest. And through that, and through a visual observation, we can potentially detect that change and therefore correspond it to the change in concentration of the analyte. Now, this is the calorimetric sensing are typically very specific. And often the dyes are designed in such a way that common interference species do not actually interfere with these kinds of measurements. But more importantly, they provide a signal in the visual range. And therefore, we can observe this with our eye or with an instrument like a cell phone that everybody has these days. And that could then provide us with the signal reporter. The problem, though, with heavy metals and calorimetric sensors are that calorimetric sensors are available, but they do detect the concentrations at the ppm level. So we have to reduce the concentration by, or increase the concentration by about 3 orders of magnitude from the ppb range to the ppm range in order to actually get good visual sensitivity to the measurement itself. So the way that we can do this is through concentration. So here is an example. So grapes, for example, can be turned into raisins. Grapes have a lot of water along with flavor molecules. By turning them into raisins, what we are doing is we are removing the water and we are concentrating the flavor molecules. So raisins are often much more flavorful. The same thing happens when we are manufacturing a product where we can take a concentrate and then that gives us a better flavor. So the sensor, which is the tongue of the skid over here, is able to detect that analyte, which is the flavor molecule that is in a concentrated form, much better, and therefore the sensor has a greater experience or detection associated with that analyte. So the idea behind this is pre-concentration. So we take something that is distributed at very low concentrations over large volumes and try to concentrate it into a much smaller form factor, into smaller volumes. If we do so, then we can use a very low-cost sensor in order to detect the presence or absence of that analyte, rather than a much more expensive sensor like ICP-MS and other methodologies. Right? So this is the basic principle. Or in other words, with our swimming pool example, what we are trying to do is to evaporate off all that water that surrounds it and reduce it into a very small volume so that I can detect the gold that is present or concentrate the gold that is dissolved in that swimming pool. Right? So the model approach that we took was, in order to use a very low-cost sensor, in our case, what we wanted to use was something like a camera in a cell phone, for instance, along with the computing power that the cell phone already has. This end can be very easily solved. In case of a transducer, the calorimetric dye gives us the transduction between the concentration and a visual representation of it, which is the color. All we needed was this pre-concentration element, a simple way, an automated way that we could actually do pre-concentration, right? So one of the things that we found that could do that was these super absorbent polymers. So where these super absorbent polymers come from, and you would have all seen these polymers, these are present in diapers, for instance, and they absorb a large amount of water, typically 300 to 1,000 times their weight in water very, very quickly. Right? So the idea behind this was to take one of these things. They come in bead form. They are commercially available and very, very cheap. Take one of these beads, put it into the solution, and when we do that, it swells. It swells many, many times its own weight and absorbs the analyte that is surrounding that. And then what you can do is you can dehydrate it or evaporate it. And this can be done by just leaving it in the sun, for example, or if you want to do it quicker, you can put it onto a stove or a hot plate. All it does is it evaporates off the water, and whatever salt that is present is concentrated. So what you see here is copper sulfate that has been loaded into this bead, and automatically when you concentrate it, you see the blue color, which was not present before, and therefore there's a visual detection even without a dye. You want to make it much more contrasting. You can add a dye that is sensitive to copper, and you see that immediate rapid change in color, and you can dehydrate that further to reduce the form factor and get a higher sensitivity. So this was the process. The nice thing is that because these beads are defined in size, it performs an automated aliquoting function. It can only absorb a certain volume of liquid, and it is going to automatically concentrate this into a smaller form factor by elimination of water. So the aliquoting in the pre-concentration is automatically defined by the form factor of the bead itself. So using this, we did an analysis using copper ions in solution. And what we find is that the same colorimetric dye, if we mix it with a liquid sample, will show us poorer sensitivity compared to that in the bead. So this is a quantitative representation of the same data. What we find is that the colorimetric dye is actually not sensitive between 0 and 1 ppm. It's primarily flat, and then it becomes much more sensitive between 1 and 10 ppm. And this is typically true for many of these colorimetric dyes. However, when we use the bead, the same dye and the same solution, now we have sensitivity from 10 ppb onwards for detection of copper. So using just this simple bead as an automatic way to pre-concentrate the metal ions, we are able to have 3 orders change in the sensitivity of this colorimetric dye itself. Now, the problem with using that whole bead is that it takes a lot of time. So basically, it took us about 350 minutes or so in order to swell this bead, and then it took us slightly lesser time to actually dehydrate these beads. And that may be okay in certain settings, but we wanted to find some additional ways of improving the performance. And so you can go to smaller bead, and that certainly improves the time, so it gets you much faster response. We also then took a core from the bead, so we basically cored it using a biopsy punch, and that provides you a smaller cylinder compared to this larger bead, and that can also perform the sensitivity as well as the large bead. But in this particular case, we can reduce the time duration of the entire experiment to under 1 hour or so. And so going even smaller will allow us to get better and better in terms of the response time of this method. We also tried other methods, like, for example, soaking instead of swelling the bead in the sample solution itself. And what we found is just soaking in 10 minutes will allow us to give us the same sensitivity as allowing it to swell for 6 hours. And that is another way to reduce the response time of these kinds of sensing methods. Our idea is to enclose this into a small device which can hold these beads, and then subsequently inject the sample, which allows the reservoir to be filled with the liquid of interest, and that will slowly absorb onto the bead itself. The remaining solution is evacuated away, and then you can dry it either in the sun or you can put it into a hot plate, and then all you do is take a camera and measure the response, measure the color, and the system will then report the actual value of concentration of these ions. So lately, we have used that method we developed for copper in order to detect for lead. So this is a specific dye that is only for lead. And what we have found recently in some of the experiments is that we are able to distinguish between no lead in the solution and a few ppbs of lead. And so this is very exciting because this is a technology that can be used by anybody in any setting. Especially one of the projects that we are involved in is in collaboration with First Nations, Six Nations here. And there's this kind of a tool will be useful for community members to actually make their own measurements and detection of their waters in streams and lakes. So we're very excited about this possibility. What we are interested in moving forward is to create this kind of an autonomous sensing platform. So far, we have this proof of concept. We want to create this autonomous sensing platform where you put the water sample in and we get a detection out of it. So building not only the hardware, but also the software for comparison and remoting purposes. And that will help us eliminate expensive equipment for resource poor analysis, setting analysis of heavy metals in water. We also want to extend this to field testing. That is the goal for this summer, if everything goes well and the lockdown is opened up. We would be testing in 6 nation communities, their water samples, and then reporting it in comparison with standard methods of measurement. So with that, that's the end of my talk. Happy to answer any questions. The image here is the dehydrated super absorbent polymer from diapers.
Thank you, Ravi, for this nice presentation. We will not be opening the floor for questions. Please feel free to put your question in Q&A section. And yeah, the last presenter for the session is Phillip. Phillip is a research associate at Center for Hydrology at University of Saskatchewan. His expertise is in field-based hydrology observations and drone-based remote sensing. Today, he'll be talking about advancing in resolving snow vegetation interaction with Lidar remote sensing. Over to you, Phillip.
All right, thank you very much. Yeah, I will be talking to you about some of the work that I'm doing on UAV LiDAR and how we're trying to resolve snow vegetation interactions from it. So we've talked, well, Jay and Chris both talked about snow and looking at it from remote sensing from sort of larger scale, you know, satellite applications. And I'm going to go a little bit smaller scale and talk about sort of the drone-based stuff. And so satellite level observations are quite good at sort of open areas, but what about the forested areas? And in the Canadian Rockies, for example, a large portion of the domain is covered in forest. And all remote sensing platforms really struggle with quantifying this critical snowpack. Most of our understanding of these areas has come from snow surveys or very small scale targeted missions and campaigns. So we don't really have a good sense of sort of the regional scale implications of forest snow interactions. But there's been a tremendous uptake in data and technologies and all that kind of stuff. So what's come about is UAV LiDAR. And so this has an advantage over, say, airborne LiDAR in that we can fly really low and really slow to forest canopies. And we can get on the order of over 100 points per square minute or per square meter in terms of our LiDAR point clouds. We have a wide range of scan angles, and this really improves the transmittance of our laser points to the snow surface. And because they're drones, we can fly these whenever we want, which can really help us target certain process interactions. The system that we're running at the university here, it's an M600 LiDAR. We've got a Regal LiDAR on it. We've got a high-grade IMU as well. And some of our work has shown that we are getting, in any sort of terrain or vegetation type, we can get snow depths to an accuracy of less than 15 centimeters. So we've been doing a lot of work at the Fortress Mountain Research Basin in the Canadian Rockies. We've been flying there since 2019. We've got 7+ scans of the place out there. They're flying again today. And it's a great laboratory, but at the end of the day, we always have to remember UAVs are still subject to weather conditions. So while this is a fantastic, calm, sunny day, that is not always the case. And so there are some limitations in how we deploy these. So we get this data. How do we get snow depth out of it? So you start off with your raw point cloud. You separate it into your surface and vegetation points. Here we're coloring vegetation points by height. Then you take your underlying ground points and you take those points and make a surface. So you have a snow-free surface. You do the same thing with your snow surface, here colored. And then you can difference those two, and you end up with a snow depth now. And because it's in the digital sphere, we can do this thing and then pull out the trees, and we can see all of the variability in our snow in terms of relationships to vegetation and also the topography. So this is on a very small scale, but we can obviously do this over our basin. And so you start seeing the variability over our entire basin, looking at the high alpine areas with large drifts and variability, and not so much in the forested parts in the lower reaches of the basin. And so this is a tremendous tool we have now that we can basically span all aspects of our landscape with the same sensor to come up with snow depth information. So what do we do with it? Well, one thing that snow hydrologists really like to do is come up with snow depth distributions. And so a snow depth distribution, it's a concise statistical representation of the variability in a basin. If we can disaggregate these into landscape units or common surface types, we end up with predictable or reproducible representations. And this is really important for models. And when we want to start driving these things forward into estimating stream flow, for example. Here's a variety of depth distributions for 4 flights that we took in 2020 and 2019. And you can see, we're not going to get too much into detail here, there's just a lot of information. And what we can start seeing is the different processes at work. So our blue, those are our rock, our alpine areas. We see this wide variability. This is because we have windswept open areas and large drifts in the alpine. So we have a large variability in the snow depth we see versus clearings. There's lower snow in the clearings, but it's not very variable because of the wind sheltering effects. And we can start looking at these things in more detail, and we can start pulling out the processes that we are seeing represented in terms of, say, interception or sublimation. But we can do this with one instrument over an entire landscape. In terms of forest snow interactions, the tree scale is where things get really interesting, and this is where it's really hard to do remote sensing. Over a forest, snow processes are happening with respect to single trees. There's interception, there's sublimation, there's unloading from the canopy, and this gives us, tree wells, shallower snow right beneath the tree. You also have processes related to the spatial variability of shortwave transmission or emissions from hot trees that will lead to very heterogeneous melt rates. These are very spatially variable processes that we really can't see from traditional remote sensing, just because there's a scale interaction limitation. But with LiDAR, we can start looking at trees and snow processes with the same common tool. The top is a canopy height model, so the hotter it looks, that's the higher your canopies. The dots are the trees that have been identified with the LiDAR. So we have all this information on our trees. Couple that with the snow depth below, and we now have this potential to start resolving tree scale forest snow interactions with this single platform, which is really quite exciting. But what about, say, let's quantify, say, a tree well and relate it to forest snow processes. What we can clearly see very quickly is that there's this non-linear dependence of tree height on tree wells, which is something we can't really understand without a ton of snow surveying or any other sort of metric, any other tool. So we can see short trees, they have very small tree wells. This is the red line. So the x-axis is distance from a tree, y is the height of the snow. So red, we have very small tree wells. There's a small indent at the beginning. Green and blue, those are our moderate trees. There's a larger tree well that develops because as trees increase in size, we have shelter from the wind and all those interacting processes. But if we go up to a large tree, at this point, we have a very weak depth distance relationship. And so this is where we're starting to see canopy characteristics, the overall canopy characteristics take over. So there's some very interesting interdynamics going on here. but it's really demonstrating that models really need to capture a canopy, tree well dynamic if we want to be able to represent the subcanopy snow depth variability, which has been a very challenging property to model. I would recommend you go look at a poster by Cobb Staines and John Pomeroy, where they dive into this a little bit more. Well, so I've talked about some accumulation process. What was snowmelt? So this is an image from a flight that we did last year between June 2nd and 5th. There's 3 days. And you can see that there's variability in our snow depth change. Our south-facing slopes are clearly melting more than our north-facing. And once again, we have this tool where we can start looking at the snow ablation process, which is governed by available energy, which is a completely different set of spatial controls than our accumulation processes. If we aggregate our landscape into our different landscape classes, the top is our clearings, that can be conifer trees, large trees, alpine areas, and the shrubland at the bottom. And we look at sort of the mean snow depth change over this June 2nd to 5th interval, and then we lump it all together by slope and aspect. We can see that we have, clearings, areas where there is no snow cover. We have this very strong control on slope and aspect on snow depth change versus looking at a forested sites where it's very muted because the forest cover is really reducing the variability of melt processes in these areas. So not necessarily new understandings, but now we have a tool that we can measure this over this entire basin, and we're not, potentially biasing or cherry picking our data points. We can look at this over an entire area. There's a couple of challenges that remain with this, well, any new tool, but the ongoing frustration is always separating vegetation from surface points. UAV lidars have very dense point clouds, so it gets a little bit hard, especially when you look at the interface between the snow surfaces and your trees very nearby. Where do you start separating those two bits? Because there's a lot of variability in the snow. But this is something that many people are interested in working on, is separating vegetation from surfaces. Another big thing, and this is more of another challenge, is that snow depth does not equal snow water equivalent, which is really what we're interested in. And so we are working on looking at some drone-based options, so top being gamma, bottom being an acoustic system. These are still in development, but there are clever ways of applying snow survey data, looking at those scaling relationships, for example. And an exciting thing is that we have another system that we have. So previously we were flying an M600 with an early version of the Regal system. Now we've got a bigger drone with a lidar that does 200,000 shots per second instead of 100,000. We were able to put a multispectral and thermal camera onto this, so we have that on the integrated platform, and it's just much more efficient, so we can fly larger areas quicker. With that, I'm going to sort of wrap up by saying that UAV lidar is a cool tool, and it gives us lots of information, but it's not a panacea. This is just one part of the integrated observing systems. We need satellite things to look at the larger scale. We need models to bridge the gaps between when we have observations. LiDAR is really good at looking at, say, small scale forest snowpack spatial variability. It's also giving us data to push new understandings of these processes, and it's going to be really quite invaluable as we want to improve and validate our spatially distributed models. This work wouldn't be possible with a whole pile of people working in the field and back in the lab processing. So I'll leave it there.
Thank you, Philip, for finishing before time. We have a quick question in the chat. So the person is asking about, may I know the wavelength and power of the laser used in the LiDAR?
The wavelength on the laser, it's 950 nanometers. So it's in the near infrared. It is, the other fun part about LiDAR is certain wavelengths of LiDAR, especially the 1500s, they tend to be absorbed by snow. So you need to get into the 950s to get some reflectance. In terms of the power, it's not very powerful. We have to be within, we get returns within 300 meters of the sensor.
Thank you, Philip. It was such a nice presentation, and thank you for summarizing it before the time. So we have a couple of questions in the chat for Jay. So if Jay can answer that in the chat, it'll be good. With that, I'd like to wrap up the session. Okay, just 1 second. I'll share my screen. This should be fine. Thank you for joining us today. We had a great conversation that will continue throughout the duration of Global Water Future program, and hopefully afterwards to ensure the research has impact it is intended to have. We also have a lot of great sessions for the next 2 days. Today we have a session on young professional mental wellness. So those of you who are interested, join that after the session. And tomorrow we have a couple of sessions related to like live poster session. We have water gallery, which is from 5 to 6. And also on May 19th, we have a couple of interesting sessions followed by the closing ceremony on 4:30 to 5. With that, I would like to thank all the speakers in this session, especially Dave, Claude, and Ravi. Thank you for the speakers, Jay, Kiana, Chris, Ravi, and Phil. And finally, thank you everyone for joining us today. I hope you find the value in joining us today. With that, I'll hand over to Nancy if there are some housekeeping items you want to mention.
Thanks, Vinay. I don't think so. I think this went really well. So thanks again to Vinay and Nastran for great chairing of the conference. Thanks to the speakers. Thanks to all the participants. We hope to see you at subsequent sessions for the conference. Okay, thank you.
Thank you.
Thank you to the speakers. Thanks, everyone.
So long, everyone. Thanks
Bye.
very much for all this. This is great.